Hello, I am Jim Levis. I'm a research assistant professor at North Carolina State University. In this presentation, I'm going to discuss life cycle modeling of solid waste processes and systems. So to start, I want to just give an overview of the solid waste optimization life cycle framework. And this is essentially a life cycle modeling tool meant to evaluate solid waste management performance economically, environmentally, while accounting for changes to the waste composition, generation, solid waste policy, the U.S. energy system, as well as potential and future greenhouse gas mitigation policies. And when you look at the figure here, we start with waste generation and composition, which you can take currently and project over time. You take solid waste management policies over time that you are interested in investigating, as well as greenhouse gas policies and energy system models. And all of this kind of input data needs to be developed and can then be input into solid waste management process models, which we'll discuss further in the presentation. But solid waste management process model are these life cycle inventory models for all of the processes in the solid waste management system, from collection to landfills to recycling to composting to anaerobic digestion. So these inventory models then develop coefficients that can be used in an impact assessment model to calculate global warming potential or smog formation or eutrophication or ecotoxicity. And so all of this together, this LCA model with all the inputs, is very useful for doing accounting mode analysis, or what we call accounting mode analyses, where you look at the environmental and economic emissions or environmental and economic impacts associated with a solid waste management system or process. But when we take those coefficients and we put them into an optimizable integrated solid waste management system like SWOLF, we can now look at all of the potential waste process choices and waste flows and try to find the best system that meets our objectives subject to our constraints over the time horizon we're interested in. And then it can tell us, the best choice of technologies, how to phase them in, where different waste components should be treated and how they should be treated, and as well as the cost, emissions, energy use, and environmental impacts associated with that system. So this is a simplified diagram of solid waste system. We start with waste generation, and then that waste is collected. It's taken to treatment and or separation facilities. This could be mechanical separation, like at a material recovery facility, or it could be thermal treatment in waste energy combustion, or biological and composting or anaerobic digestion. The recovered materials can then be taken to material reprocessing and recycled into new materials, and the other materials, your residuals and things, can then be disposed. So this is a broader diagram of that shows all the interconnected effects and processes in the solid waste system. We have different types of collection, whether you're doing commingled recyclables, mixed waste or residual collection, or organics collection. Your recyclables can be taken to some sort of commingled material recovery facility, and then they'll be separated out to material reprocessing. You could also separate out your combustibles and send those to thermal treatment. And then these black lines are different residuals that can either be combusted or landfilled. Your mixed waste residual waste can go to a mixed waste material recovery facility, where you can also recover recyclables or combustibles, and it also creates a residual stream that can be combusted or disposed. And the mixed waste MRF, or it can also be called an MBT plant, can also create an organic stream that can be digested or composted. And then if we take our organic stream, that stream can go to anaerobic digestion or composting, depending on the purity and the processing. You can create a beneficial soil amendment, and then it also creates some residual that can be thermally treated or go to landfill. Materials that are thermally treated and waste to energy, you can recover the metals from the bottom ash, and you can also recover the bottom ash, and that can be used as an aggregate. And then you can also dispose of fly ash and or the bottom ash in an ash landfill or a regular landfill. And this kind of shows all the different potential interconnections between still a pretty basic solid waste management system. When we look at current solid waste management in the United States, these are just two different estimates that are actually pretty close to each other. The majority of waste is currently landfilled, with about a fifth to a quarter of it being recycled. Between 6 and 9% is composted, and between 7 and 12% is combusted for energy. Whenever we're looking at the functional unit for a solid waste management process or system, we need to determine it based on what we're actually analyzing. What are the answer we want to get? And this needs to be consistent with your goal and scope definition. Well, this is part of your scope definition, and for more information, you can review our Intro to LCA presentation. So for one example, what we often do in SWOLF analyses is we could look at the mass of MSW generated in, let's say, Wake County, North Carolina over the next 30 years. So whenever you're doing these kind of stage-wise analyses that SWOLF is capable of, you have to look at your entire system over some time frame. Often you'll see life cycle assessments of solid waste management processes are static analyses. There's usually 1 ton of some baseline material that can either be generated or be at the gate of a facility. When we're looking at a solid waste management system, we have to look at how our waste is generated. So in our modeling, we have, in the SWOLF model, there are 3 different types of waste generation sectors: single family, multifamily, and commercial. The user defines the number of each one of those sectors, and then there are inputs for each sector based on its type, the population, number of stops, generation rate, composition, what collection service is offered, and what destinations are possible from that sector. And there's more information on that if you look at our collection process modeling presentation. So like I said on the second slide, the solid waste management life cycle inventories of each solid waste management process are the foundation of all of this life cycle modeling for solid waste management. The process models we use are developed from the bottom up to determine the cost, emissions, environmental impacts associated with each process in the solid waste management system in consideration of the waste quantities and composition going to that process. What we mean by bottom up is that we're looking at all the sub-processes in that process and developing those emission and cost estimates from how all those sub-processes are connected. So something like a MRF, we would look at the number of conveyors, the electricity use from the conveyors, the electricity use from the different optical sorters or eddy current or magnets or the baler, and combine all of those to get the overall life cycle inventory for the entire material recovery facility. And then these process models are then linked using mass balance equations to develop models of the entire system. The current included processes include waste collection, transfer stations, material recovery facilities, anaerobic digestion, composting, recycling, landfills, waste to energy, etc. So this is a generic process model just to get an idea of how these are connected. We start with something like the user inputs on the left and some incoming waste stream coming in from the top, and this is a generic process model. So coming out, so there could be some stored mass in there for like a landfill, and then coming out the bottom we have some physically separated materials or biologically or chemically transformed materials like ash or compost, and then coming out the right we have all of our emissions from direct emissions or equipment use or electricity use, as well as our capital and operating cost. And then these process models determine those downstream mass flows. So what's coming out the bottom here determines what goes down into the next one. So if this is a MRF, what gets separated out, what's in our recyclable stream and our residual stream, then determine what ends up going to the landfill and what goes to material reprocessing. So this is for the integrated solid waste management system boundaries. When we look at our entire system from a life cycle perspective, we start with municipal solid waste coming in to our solid waste management system that I showed a couple slides ago. Our solid waste management system has some direct gross emissions, things like tailpipe emissions from collection vehicles or landfill gas emissions, but then there's also electricity, fuel, raw material extraction and processing used in the solid waste management system, and then electricity, fuel, and raw materials has emissions associated with it. And then in our solid waste system we can also generate electricity or compost or recyclables, and then each one of those has benefits and leads to avoided emissions. So whenever we're looking at our solid waste system, we have to recognize that it is interdependent with the electricity system. And in North America, well, in the US and southern Canada, there are 9 different regions for electrical grids, and each of those electrical grids has different fuel shares and therefore different emissions associated with it. So the emissions associated with our solid waste system are going to depend on what region of the country you're in and what are the essentially how clean the electricity you're using or your offsetting is. So these values show basically the greenhouse gas intensity from each of the regions shown in the country. They're called NERC regions. And basically, the cleanest region, this NPCC, which uses a lot of hydro, is has less than half the emissions of the dirtiest region, which is the Midwest Reliability Organization. And you'll see the national average is 0.71 kilograms CO2 per kilowatt hour. And there's a few like the Reliability First Corporation and CERC and FRC and TRE that are pretty close to the national average. And then the western coast is a little cleaner, and SPP is essentially the same as MRO. So this is something you need to consider, especially when you're looking at energy generation from landfill gas to energy or waste to energy. And this is an illustrative comparison between landfill gas of landfilling and waste to energy of mixed waste. And basically what you see is if you have a high electricity offset, then waste to energy performs significantly better than landfill, and as the electricity mix gets cleaner, as what you're offsetting is cleaner, waste to energy, well, both of them do worse, but waste to energy is affected more because more of the benefits of waste to energy are tied to electricity generation, where a lot of the greenhouse gas benefits associated with landfill are due to carbon storage. And then these results are just meant to be illustrative that shows where the grid is matters a great deal, and this matters a great deal as we think forward because most people expect the U.S. Greenhouse gas intensity from electricity to be going down, so that could affect where and when and how waste to energy is and how effective it is. And this also interplays with how our waste composition is changing with time as we shift away from paper and plastic. As we shift away from paper and increase our load of plastic, that's also going to have an effect on combustion emissions over time. Finally, I would like to acknowledge the National Science Foundation and the Environmental Research and Education Foundation for their support of this research. If you're interested in SWOLF or life cycle assessment, please check out our other videos. Thank you very much.